lecture is going to be a bit of a grab bag because there's a bunch of ingredients that we need to get onto the table to set up for the stuff we're going to do tomorrow. So there's going to be a few different pieces going on, but then hopefully by tomorrow you'll see how these are all coming together. So the first thing I want to talk about a little bit is this issue that Bob alluded to this morning, which is what is equality of programs. And I'm not going to say very much about this, but I do want to say a little bit more than we've said so far, because it's going to come up in a few places today, and we're going to need to have a little bit of a framework for talking about it. So there's, in my mind, kind of two different ways of thinking about. So imagine you wanted to define something like E is equal to E prime in tau, which means that E and E prime are the same in some sense as programs. Okay, so how would you think about this? In my mind, there's kind of two different ways that people think about answering this question. So way number one is to axiomatize, not sure if that's enough, some class of mathematical models of programs and then you say that two programs are equal if the equation is true in all models. And these days, these models are usually described using what's called category theory, which is a branch of very abstract algebra. It's kind of abstract algebra. And it's a way of kind of setting up stuff. So in category theory, there's the notion of a map. And if you have a program that's like gamma says E has type tau, then you interpret that mathematically as what's called a map from the interpretation of the context to the interpretation of a type. Okay? And so you can think of this as including kind of denotational semantics, if you've seen denotational semantics of languages in CPOs or something like that, or set theoretic models of your language where you interpret a type as a set and your maps are set theoretic functions or something like that. So you can kind of phrase a world of things in this sort of way. And so the reason that I want to bring this up is that there are certain abstractions that come up in this kind of abstract setting of category theory that we saw this morning in programming terms. So for example, in this kind of setting, you can talk about what a product is, and it's just going to be a paraphrase of the rules that we saw this morning for product types in a different notation. So a product type, if you write it out, I mean, it's not, this is mostly just for culture, but if you write it out, is a thing, tau1 cross tau2, which has maps to tau1 and tau2, which we can call, I'll just write it out as first and second. I think Bob was using 1 and 2 for this morning. Okay, so what is a product, right? Think about the product types we saw this morning. It's a type. From the product of tau1 and tau2, you can get a tau1, and you can get a tau2. And then the way that you make a product is pairing. And if you draw that as a picture, what it says is, if you have a term E of type tau1 and a term, let's call it E1 of type tau1, and a term E2 of type tau2, right? That would be like if I have gamma proves E1 tau1 and gamma proves E2 tau2, then gamma proves E1 E2 is in the type tau1 cross tau2. And the way that you phrase that here is that you say that there exists a unique map here from gamma to tau 1 cross tau 2 that makes these triangles commute. And what does making these triangles commute mean? It means that if you do this and then you take the first projection, you get E1. And if you do this and then take the second projection, you get E2, which is to say that if you think of this unique thing that exists as saying that this thing exists and it's unique, then what you're getting out of that is there is a pairing operation that satisfies the beta reduction rule and satisfies an equational principle here, which says that this is the only thing that fits here. And if you work out what it means to be the only thing that fits here, then one way of saying it is that you have the equation E is equal to the first projection of E and the second projection of E paired back together. So in this setting, we can think about this, in this mathematical setting, we can think of this equation coming up, right? So like, if you don't get the diagram, that's OK. I'm just drawing the diagram for culture. But what happens is that the diagram gives you a spec that comes up in many mathematical models for what a product should be. And it includes all of the things that Bob said this morning, including you have pairing and first projections and the step rules that say first of E1, E2, steps to E1, and stuff like that. That's coming up in the fact that the diagram commutes. But also this idea of what's sometimes called an eta rule or extensionality principle. And if we think about the eta rule or extensionality principle in this case, what it's saying is that a pair is determined by its first and second projections. Right? The only information in a computation of a pair is what you can get out of it by first projection and what you can get out of it by second projection. So in particular, if you have anything else that behaves the same under first projection and under second projection, then that's really the same program. Okay? So this is going to come up in a little bit because we're going to talk about, does a language have pairs? Right? When you ask, does a language have pairs, the real question you want to ask is not just, does it have some notation that looks like this and this and this, but does it have the beta rule and the eta rule? And you might say, well, it has pairs with a beta rule but not an eta rule. You could call that a weak product or something like that if you were in that kind of setting. But when you're thinking about, do you really have the type, you want to be thinking about, do you have the type and which equations do you have? Okay? And continuing with the duality from this morning, you can turn this all around and do what's called coproducts. And so then we'll just turn the diagram upside down and say that tau 1 plus tau 2 doesn't have maps to tau 1 and to tau 2. Instead, it has maps from tau 1 and from tau 2. So I think Bob was calling these 1 dot and 2 dot. And then if you can map from tau 1 and tau 2 into some other type sigma, then what we get is that there exists a unique map here. And so notice there's a nice symmetry between the product and the coproduct here. And what this is telling you, one sec, is that you have the injections into the coproduct, and then this mapping out principle is giving you case analysis. So if we look at what's going on there, it says that if we have an f from tau 1 to sigma and a g from tau 2 to sigma, then what we get is a case of fg as a function from tau 1 plus tau 2 to sigma, which is half of one of the type isomorphisms that Bob had on the board this morning. Okay? And then, of course, because we said there's a unique thing here that makes these triangles commute, well, commuting is the fact that case after an injection goes to the appropriate branch, which is one of the step rules. But we also have a uniqueness principle that says that anything that fits here, making this commute, is equal to the case. And if you unwind what that means, I'll just do a few special cases of it. Remember that bool is 1 plus 1. So in particular, this mapping out principle, this uniqueness principle, should tell us something about maps out of bool. And in particular, it'll give us things like lambda underscore dot true is the same program as lambda x if x then true else false. So as functions from bool to bool, these are the same. Wait, sorry. Those are not the same. These are the same. Got my two examples mixed up. OK, so why are those two functions the same? Well, one of them takes in whatever it's given and gives it back. The other takes in whatever it's given, looks at it. If it was true, it gives back true. If it was false, it gives back false. Well, on true, this gives back true. On false, this gives back false. On true, this gives back true. On false, this gives back false. These things are both two things that fit here and make this diagram commute. Therefore, they're equal in this idea of a coproduct in a mathematical setting. Okay? It makes sense in programming terms. So the other example that I was going to do is, what about lambda underscore dot true and lambda x if x then true else true. So if I have the constantly true function on the one hand, or I look at my argument, and no matter what the argument is, I return true function on the other hand, then in this kind of extensional sense, both of these will return true on all inputs. Both of these make this diagram commute in the same way. And so we get that they're equal in this sense. OK? So those are some things you would expect out of an equation for a sum type. Yeah?
Okay, so about these two diagrams.
Yeah?
In the upper one, you can see you wrote gamma.
Yeah.
But it's not in the lower one.
Yeah. So really, it's a bit subtle. But if you want to really kind of say independently what's going on with a coproduct in a programming language, it sort of includes the fact that you can do that carrying some other stuff along, which is not the default axiom for a coproduct in category theory. This turns out to be the same if you have function types, because you can always shuffle the gamma off into a function and not worry about it. But if you wanted to do that, then you would sort of carry the context along here. So I'm just, the category theory here is really just for culture and just to see that you can draw pretty pictures and things like that. So if you didn't get it, that's OK. Yeah. 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 So it's explicit. The real difference here is that in intuitionistic logic, there's an asymmetry between premises and conclusion because you have many premises but one conclusion. And that sometimes breaks the symmetry of these kinds of things. Yeah, we can talk about it more during the hands-on session. There's something else.
How is the diagram for void and unit?
Sorry? How the?
Void and unit.
Oh, for void and unit? So for unit, it looks like that. There's a unique map from anything into one. And for void, it looks like that. There's a unique map from void into anything. OK? Which is just the zero-ary case of this and this, respectively. OK. So that was just to boot up on what one might expect from products and sums. And the main thing is you might expect or should expect eta rules like this and like this. OK, so that was one kind of notion of equality. So generally what people do if they're thinking about equality of programs is they'll either kind of have this picture in mind where there's a whole class of mathematical things and an equation should be true in all of those mathematical things. Another perspective you can take is that, well, I don't really care about a whole class of things. I'll say there's one true model And often, if you're going this route, the one true model will be an operational one. And then you can think about equations being true if they're true in that model. Okay? And what I mean by an operational one, we're not going to get super precise about this today. But the main thing that I want to bring up is what's called contextual equivalence. And what that means is that two programs are equal if and only if for all contexts C, when I fill that context with E, it's equal to filling that context with E prime, where C is a context that takes whatever type to, let's say, bool. Okay? And so what is this saying? So if you go through the details, we can make all of this precise and talk about exactly what a context is and stuff like that. But the idea is that a context is a way to take a program of an arbitrary type and embed it in a bigger program that returns an observable answer. And for our purposes, let's just say the observable answers are true and false. And so what we're going to do is we're going to take our program of an arbitrary type and embed it in a context that gives you a true or a false. So if, for example, tau is int arrow int, then an example of a context might be C takes the function f is defined to be apply f to 0 and then check if that's even or something like that, right? So if you have a function from numbers to numbers, you can't observe the function. What you can do is you can apply it to a number. Well, we're going to say you can't even observe the number. Let's just reduce it all to bool. And so what you can do is apply it, check if it's even. So you get one bit of information. But if what you're saying is that two programs are equal if and only if they work for all contexts, then in fact you can observe the whole number eventually by just applying enough context that you get to see every bit of the number. So the idea here is that contextual equivalence says two programs are equal if you can't tell them apart, right? If there's no observation that lets you distinguish them, then they're equal. And so this notation here just means they have the same value, let's say. This is going to get a little bit more subtle once we get to divergence and other effects and stuff like that. But for now, think of it as they have the same value. They both return true or they both return false. OK? And there was a question. Yeah.
I was going to ask whether it makes a difference that we can only observe a finite number of bits.
Well, so you have to observe at a type that's sort of data, right? So you could make it be nat or something like that. But that gets a little subtle. But yeah, okay. yeah.
So in the context,
Mm-hmm.
there are only two maps from tau to bool.
So from tau to bool. So tau might be int arrow int, which means there's infinitely many maps from tau to bool, right? Because I can apply this to 17 or whatever.
Right.
Yeah.
So in that case, I guess I'm still a little unclear on these lot of categories for that picture.
Uh-huh.
When you have a morphism from gamma to
Yeah.
what?
So morphism from gamma to program, right? That's a program of type tau in gamma.
So what's the state?
Yeah. So what this is doing is it's just saying, I want a way to embed my program in a kind of complete program, right? So think of the context as main, right? So I have my program, and then outside of that, I have like the part of the program I'm interested in, and outside of that, I have some context that's sort of the main function that sets it up and runs it. That's a way to think about it. Yeah.
What do you mean by C value when
Well, so if these are both of type bool, what that means is either they both evaluate to true or they both evaluate to false. Right, so that's why it's important that this is bool, an observable type, not a function type. So I'm defining this by saying that they're the same in any context that produces a Boolean. Right, so for any two programs, they're equal if whenever you put them inside of a main function that calls them and then eventually outputs a bit, you get the same bit.
okay.
Yeah, so you avoid that answer in exactly that question in exactly this way. Okay, so are we kind of at a hand wavy level good on what's going on here? Right, so the main thing you want to think about is what we're going to need later out of this is the idea that two programs are equal. You can think of that as whenever you embed them in some complete program, you get the same answer. Okay, that'll be a helpful intuition later on. Good? Okay, so I want to use that now in a study of recursion first and recursive types second. Okay, so the first thing to say is if we go back to the kinds of examples that you were doing from the hands-on session yesterday, then we were writing programs like, I don't know, double takes is a function from the natural numbers, and if you write it out as a pattern matching function, double of 0 is equal to 0, and double of successor of n is equal to 2 plus double of n. And the thing I want to emphasize is that here, the termination happens to be obvious. Right? Why does this terminate? Well, it fits the template of structural recursion that you were playing with the recursor in the hands-on session yesterday. Right? Which means that when you write double on 1 plus n immediately recurs to double on n. And so we're just doing structural recursion on a natural number. All right. Now, there was the question that came up in Slack yesterday that I think someone posted to Piazza that came up in the Slack discussion, so maybe people saw it, about what happens if you try to write the GCD function instead from takes two natural numbers and returns a natural number. So a nice way to do this is as follows. The GCD of m and n is equal to, what you want to do is you want to test how m and n compare. And since we now know about sum types, let's not just return a Boolean, but return one of three possibilities, right? So I'm going to define not just bool, which is 1 plus 1, but the type 3, which is 1 plus 1 plus 1. And I'm going to give the constructors suggestive names like equal or less or greater, which gives you a trichotomy principle, which says if I have two numbers, then either m is equal to n, m is less than or equal to less than n, or greater means that m is greater than n. And in these three cases, well, what's the greatest common divisor of m and m? It's m. And then I always have to do the math to convince myself that this is true. But what's the greatest common divisor of m and n if m is smaller? Then it's the GCD of m and n minus m. Why is that? Because you're preserving divisibility by subtracting off there. You're basically counting down by one multiplication, one addition. And so if it's the other case where n is smaller, then we can subtract off n from m and keep n the same and go on. OK, and so the fact that this implements GCD is not the important point for right now. The important point for right now is that it has a different pattern of recursion. Right? It doesn't just recur on a number that's one smaller. Right? It recurs on a number that's arbitrarily much smaller in two different ways in two different cases. Okay? So the question was how to code this in Gödel's T. Did anyone come up with an answer? So there's a couple of different things you can do, right? So the question is, what do you do if you have a function whose termination is not manifest, and you would like to code it in a language where the termination of all functions must be manifest? Well, there's a couple of options. One, you could give yourself a gas tank, okay, which means an extra number that you decrement in every recursive call. So basically, add in another argument k, and here you get k minus 1, and here you get k minus 1. Yeah?
But there isn't a particular argument that we're always counting down on.
Well, I'm saying we're going to add a totally separate other argument. So in addition to this, this is going to take a whole nother number and make it be structurally recursive on that. Well, now it's structurally recursive. OK. What do we need to do to get our original function out of this? We need to pick a particular amount of gas to put in the tank at the beginning, such that we always have enough gas left in the tank through all of the recursive calls we want to make. OK. And how many recursive calls do we need? Well, we can probably bound it by something in terms of m and n, like the maximum of them or the sum of them or something like that. OK? So one option would be to give yourself a gas tank and count down like that. Another option, which is basically the same idea, is to, like, rather than having a separate gas tank argument here that decreases, you could use one of m or n or both of them as the gas tank, and then do some logic where if you're in a spot where you're sort of in one of these intermediate states in between these two, instead of actually doing what you're doing here, what you would do is like just kind of stand still and go to a recursive call that says, keep going through this intermediate state until I hit the spot. So basically, you would loop through the fact that, loop through this until you get down to n minus m, and then at that spot, return to the real code. OK? Another option that you can do is to compute a memo table, right? So rather than computing the GCD of m and n, which is going to give you back a number, what you would get is a list of numbers which represents all possible recursive calls. OK? So imagine that, think about dynamic programming or something like that. Instead of computing just the GCD of m and n, I will compute the GCD of all numbers from 0 up through 0, 0 up through m and n. Well, if you do that, then whenever you want a particular recursive call on something that's smaller, that recursive call will be available to you because you will have previously computed all possible recursive calls that you might ever want to run into. OK? So these are all strategies for coding recursive functions that have a different recursion pattern than the basic one in a language where you're trying to make things total. And it's fine, you can do that. But one thing that's a little bit unsatisfactory about these sorts of things is that there's problems with both the structure and the efficiency of these kinds of encodings. So in terms of structure, I mean there's problems with the way the code looks. right? We took a nice simple function, very clear, and then we added this weird gas tank argument and said that what we're going to do is we're going to count the gas tank down. And so like, what's that doing in the code? Why is it there? You don't really want to read that. Moreover, in this example, it was pretty easy to eyeball like how much gas to put in the tank at the beginning. But in other circumstances, it can be much harder. We're basically proving that the function terminates by proving that that will always be enough gas, right? So then there's a proof obligation off to the side that says, really, this computes the same thing as the original GCD function. And where that goes in that version is saying that you definitely know that you have enough gas in the tank. And for GCD, it's sort of intuitively clear that like you can bound the amount of gas that you need. But if you have a different problem where the structure of it is harder to eyeball, then it can be a lot of work to prove that you actually have enough gas in the tank to finish the problem, right? If you give this kind of truncated, give yourself a gas tank thing, and then you put in 0 here, then your program will always just stop or something like that. So yeah, I guess I should have said that like GCD does this, but also if you're out of gas, it just has to return some junk value or something like that. Okay, so like you kind of gum up the code with if you're out of gas, return some junk value. Maybe there's not even a junk value that you could possibly return. It gets complicated. Okay, so that's a problem with structure in that one, meaning the code doesn't look nice anymore. In terms of efficiency, well, in this version, we're doing the check on the gas tank. If you do the standstill implementation, then you're taking the function that you wrote in a clever way in order to make it more efficient, right? So if you do this kind of thing, then it's more efficient than just counting down by ones. And if you do, you can do a mod thing that's even more efficient and gets you like log or something. Then you'd lose that if what you're doing is recurring by ones, standing still, except in the key cases where you actually would have done the original recursive calls, and in those cases, actually doing the work, right? And you're taking something that would be sublinear asymptotically, or at least sort of better than linear in terms of a constant factor because it counts down more quickly, and you're making it linear again by counting down by ones. Okay? So that's bad from an efficiency point of view. And if you go all the way to the memo table implementation, then you're taking something that would be linear or something like that. And I guess in this case, the dynamic program works out such that it's not too bad. But if you imagine other functions, it might get exponential because you're computing all possible recursive calls instead of just the ones you'll happen to need. And then in a constant factor sense, you're computing all possible recursive calls and storing them, right? So think about space. At least in terms of space, you're computing all possible recursive calls and computing this big table of them, when in fact, you actually only need 1 or 2 in each case. Okay? So this is kind of talking about the pros and cons of making termination manifest as opposed to not. Okay? And because there are these kinds of trade-offs, what we want to do today is to start to think about a language where termination is not manifest. That is, we're going to allow our programs to infinite loop, in which case we won't have to worry about these kinds of issues. We'll have to worry about other kinds of issues, but not these. So the idea is to add non-termination to our programming language. And the way that we'll do that is to talk about general recursion as a language construct. So what this means is may not terminate. So unlike yesterday when we proved that all programs terminate, today we'll set things up such that not all programs terminate. Okay. Of course, we'll mostly be interested in the programs that do terminate, right? Like we're sort of allowing more stuff, though most of the programs we write will be ones that terminate or ones that at least we intend to sort of what's called co-terminate, which is something that comes up when you think about the dual to inductive types, which are co-inductive types, which means that if you think about something that's like a process that's running, you might not want it to finish, but you might want it to always be responsive to input after a certain amount of time. So that's called productivity. Yeah.
Just before you get on to the non-terminate,
Yeah.
I just was wondering about one comment that Bob made, which was you really have to somehow bake into your program
Right.
strong induction.
Yeah, so this was different ways of baking strong induction into your program. Yeah. Yeah.
What if you have this lemma of strong induction over here?
Yeah.
You just cite that in your program. You don't have to unwrap the whole.
Yeah, I mean, so I don't know if Edwin Brady will talk about this, but there are sort of ways of taking this idea and making it more efficient that people use in dependently typed languages that, yeah, like you sort of, yeah, yeah, yeah. I mean, so it's not like you can't possibly write an efficient program in a total language. It's like, just saying there are tricks you can play, and then there's a question of how do you make the code nice and how do you make it efficient, and I don't think there are like perfectly satisfactory answers to all of that. One thing you can do, which has other nice consequences, is just say, well, let's give up and allow non-termination. Another thing you can do is do research to make this kind of thing more palatable. Yeah. OK, good. Yeah.
We want to compare, for example, program that do not terminate.
Yeah.
So, for example, do we need things like simulation?
Yeah. So equality will get subtle here, and I'm not going to like do in technical detail how equality works, but I will point out some subtle things. Yeah. OK. So first of all, let's set ourselves up. So the basic idea is that in this setting where programs may not terminate, call by value / eager is very different from call by name / lazy. Okay. Yesterday and this morning, when we introduced these things, it was kind of just a choice whether things were eager or lazy, whether things were called by value or called by name, because when everything terminates, it's really just a matter of efficiency in terms of the difference between the two. Right? The program will take different steps if it's called by value than if it's called by name, but you'll get the same answer because everything terminates, and you can prove that you'll get the same answer. When you have non-termination, suddenly the order in which you run things starts to have dramatic consequences for what sorts of things you get in your language, because you'll be able to tell the difference in the evaluation order by looking at which things terminate and which things don't. And so equality gets much more subtle here, and the distinction between call by value and call by name gets much more important here because it influences the behavior of programs and not just the efficiency of programs. Okay? So let's first look at the call by name / lazy case, and then we'll think about how that adapts to call by value eager. Okay, so in call by name lazy, here's a quick summary of how to get yourself going with general recursion. We're going to add a new thing, which is called fix x is e, and really I should write fix sub, or let me write it as fix x colon tau is e, which is going to be a program of type tau for any tau if, assuming x is tau, e has type tau. So assuming you have a tau, e is a tau, gets you a tau. And there's only one dynamic semantics rule for this, which is that fix x is, and of course, x here is bound in e. Fix x is e. What does that step to? It steps to e with fix x is e replaced with, substituted in for x. Okay, so what is that, and how does that give you general recursion? Let's look at some examples. How do we write the GCD function using this? What we'd like is a GCD function of type nat cross nat arrow nat. And remember, the way we wrote it out before is somewhere in the middle of it, we want to be able to call GCD on m and n minus m, or something like that, right? Like the actual code no longer matters. The point is, like, somewhere in the middle of this function, there's that recursive call. Okay? So the way we're going to define it is fix GCD prime of type n cross n arrow n is lambda of n and m dot the code we had before, where eventually in the middle of it, we'll call GCD prime of m and n minus m. Okay? So what are we saying? We're saying, let's assume, right? So GCD prime here is a new variable, right? And what this does is it stands for the recursive calls. Okay? So what we're doing is we're saying, suppose you have a GCD prime of type n cross n arrow n, then what you need to do in this part here is to write a function from n cross n to n, if you unwind what the fix rule is saying there. So the fix rule is saying, for any type, if you assume an element of that type and produce an element of that type, then you get an element of that type. Okay? So the way you want to think about it is, assuming we have a recursive call, we write the code using that variable in place of the recursive call. Make sense? It's like what we saw in the recursor yesterday, right? In the recursor we said, assuming we have a variable that stands for the result of the recursive call, we write the code. Here we say, assuming we have a variable that stands for the entire recursive call as a function, we write the code. Therefore, if this is a function, we can apply it to whatever arguments we want, including things that are not structurally smaller than the inputs to the original function. Good? OK. So now, what's the thing that we want to be true? The thing that we want to be true is that when you call GCD on a particular n and m and n, then eventually that should step to GCD of m and n minus m, assuming that's the appropriate branch of the case analysis that we wrote a few minutes ago, right? So at some point, we want that if we define the whole GCD to be this term, then here we want that GCD of mn in the appropriate case steps to that recursive call. Okay? Why is that true? Well, if you look at the step rule for fix, what it says is you take the whole fix and you plug it in for the variable. What is the whole fix? The whole fix is our definition of GCD, which means that what will happen is that when we run this, GCD itself takes a step to lambda nm goes to GCD prime of m and n minus m, right? This lambda with the whole GCD code plugged in for GCD prime, right? Where GCD here is really an abbreviation for that whole expression. So we take the whole recursive function and we plug it in for the variable that stands for the recursive call. And so, of course, what this substitution does is it wipes away the substitution and throws this whole code in here. So what we'll get is a copy of this whole expression at all of the spots where we would have made recursive calls. And then when we get down to them, what we'll do is we'll run that expression again. So by adding this self-referential operation, right? So the reason that it's called fix is it's what's called a fixed point. You're making a self-referential expression where it itself gets plugged in for the variable that stood for the recursive call. Okay? This self-reference gives you the ability to make these kinds of recursive calls. Make sense? Questions? Okay. What else can we do with this? So we showed that we can define a general recursive function like GCD. Let's tick off a few more things that don't exactly have the form of recursive functions. Because notice that we can do recursion not just at type, not just at function types, but also at other types. So for example, I can write fix x colon tau is x, which has type tau, because assuming x has type tau is the identity axiom that tells us that our consequence relation has an identity. So what is that? Well, how does it step? If I have fix x is x, that steps to x with fix x is x plugged in for x, which is equal to fix x is x. OK, let's try it again. Which steps to x with fix x is x for x, and so on. OK? So if I write the fixed point of something, fixed point of the identity, what I get is an infinite loop. OK? So sometimes we'll write this as bottom for infinite loop. OK, so we've demonstrated to ourselves that we have non-termination from fixed points. What else can we do? Let's try fix x colon nat is successor of x. Well, that's of type nat because assuming that x is of type nat, successor of x is type nat. And what does that do? So this steps like this. Fix x is successor of x, steps in one step to successor of fix x is successor of x. Does it keep stepping? Or is it a value? Right. So we said we're in call by name lazy for now. Right? Okay. So this is a value. But if you ever do a natrec on it or a nat case on it and peek at this, what'll happen when you run that? Then subsidiarily, this will be successor of fix x is successor of x, and so on. Okay? So what you have here is essentially, it doesn't actually run to this, but you can think of it as successor of successor of successor, and so on. Right? So what we've written here is an infinite tower of successors. So somehow we've got a new natural number that we didn't have before. Or another way of saying it is that our natural numbers aren't really the natural numbers anymore, because there's another thing in that type that's not 0 or successor of dot, 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 applied to 0. Right? Somehow we got an infinite value in our type out of having fix in the language. And so we can do similar fun things like, what if you do fix x colon nat list is 1 cons x. What is that? Yeah. So it's a list that never terminates with a nil of ones. What if you do fix x is 1 cons list map of 1 plus on x? So I start with 1, and then, right? So if you unwind what this steps to, you can think of it as 1 cons 2, cons 3, cons 4, cons 5, all the way out, right? So what I've got there is numbers starting from 1 as an infinite list. Okay? So if we have general recursion and a lazy call by name interpretation of things, then suddenly what looks like natural numbers are really something else. And what looks like lists are really something else. In particular, there's infinite stuff. People often call that streams, though sometimes streams mean things that must be infinite, whereas if you just take lists here, it's things that are either finite or infinite. So you have to be a little bit careful about the terminology there. But suddenly everything changed in the sense that our types have more things in them than they had before. Okay? So that's what I mean about it being behaviorally important, whether something is a eager or lazy here. Okay, so good. Oh, one more, I think Bob mentioned. What if you have fix x colon tau 1 arrow, what was it? Tau 1 cross tau 2 arrow sigma 1 cross sigma 2 is some stuff. Well, call this, right? If you have a fixed point of a function from a, sorry, that was supposed to be a plus. Fixed point of a function from a sum to a product, that's a now recursive object, right? Think of the variable standing for this as a variable standing for the object itself, which is a tuple of functions, or a function from a sum, whichever way you want to factor the matrix, and now you've got recursive objects in the game. Okay, so there's lots of fun stuff we can do if we have general recursion. So now what I want to come back to is the question of, do we have products and do we have sums in the sense of what we were talking about a few minutes ago in the beginning of the lecture? So suppose we're in a call by name / lazy setting. Question, do we have products? Which amounts to the question, if I have an E of type tau1 cross tau2, is it the case that E is equal to the pair of the first projection of E and the second projection of E? So if you think about, E is a pair, right? So imagine that this is like 1, 2, or something like that. Then this makes sense, right? Because this is the first of 1, 2, and the second of 1, 2, and that's 1, and that's 2, and so it makes sense. Right? So if you feed this, if you're asking this question about something that's literally already a pair, then it's just the stepping rules sort of tell you that this holds. So the main thing we want to think about is suppose that E here is bottom, i.e. an infinite loop. Is that the same as first of E, second of E? That is the pair of first of bottom and second of bottom. Yes? Okay. This is what's really subtle about lazy programming with divergence. These two are the same. One of them is an infinite loop, and the other is, in a certain sense, a value, and yet they're the same. The easiest way to see that is to come back to this idea of contextual equivalence that we talked about before. Okay, so what should it mean for two programs to be equal at type tau1 cross tau2, right? That's what we're asking about here. Two programs of type tau1 cross tau2. The thing that gives us some flexibility is that we're not saying they're equal in tau1 cross tau2 if they both reduce to a value and they have the same value, or they both infinite loop, or something like that. What we're asking is, what can we possibly do with such a thing? Well, if you imagine all the contexts that you might put an infinite loop in versus all the contexts that you might put the pair of first of an infinite loop in or second of an infinite loop in, there's a ton of programs out there, and you can put these two programs inside of all of them, right? There's a ton of contexts out there. You can put these two programs inside of all of them. But if you think about what you can do with a pair, right? What this context is going to do with this thing, because this context has to accept things of a product type and take them to Booleans, essentially, all that context can do is apply a first projection or apply a second projection and then do some other stuff, right? The immediate ways to access a pair are only first and second projection, which gets you to the idea that somehow we're considering all contexts, but really it suffices to consider what happens on first and second. And so if we take the first projection of bottom, is that the same as the first projection of the pair of the first projection of bottom and the second projection of bottom? Well, yes, because that will take a step, just like we said before, to the first projection of bottom. Okay? So the infinite loop at pair type is really the same as the pair of two infinite loops, first and second. Okay? The reason is that all we'll ever do with this thing, which has pair type, is apply a first to it, or similarly, apply a second to it. Okay? So equality gets much more subtle here, because naively you would think about it as one program that infinite loops should never be equal to a program that terminates. But in a certain sense, if you just read these operational semantics literally, this will infinite loop, and this will terminate. On the other hand, if you look at how these behave inside of a closed program that takes you down to Boolean type, you can never tell them apart. Okay? So you can sort all of this out. So there's a lot of work by Paul Levy and Noam Zeilberger and lots of other people, where if you use a notation and use a type discipline that makes it more obvious what's going on, this kind of like weirdness gets less weird. And so there's lots of work that kind of sorts out this issue of evaluation order. But the key thing that's really going on is that when you're talking about, just one sec, yeah. When you're talking about a program in a lazy or call by name language, the way that you want to think about it is that such a program, if you think about a program as being x1 tau 1 through xn tau n proves e colon, you want to think about this as over here, not really a value of sigma, but a computation that may diverge of a sigma. And if you sort out the fact that computations of a sigma are really a different sort of thing than what you expect out of like a naive kind of set theoretic interpretation of a sigma, then it really makes sense that in such a sense, the computation that diverges is the same as the computation that takes first and second projection, pairs them back together. Yeah.
So trying to map this back to Haskell,
Mm-hmm.
I define E in terms of itself.
Yeah.
And I define E prime in terms of first and second.
Yeah.
And my context is a pattern match that always appears unit.
Right.
One will loop forever, the
Yeah.
other will
Right.
return unit.
Right. So that's because pattern matching is doing something different, which is forcing projections, right? So that's because like Haskell's like, let's talk about it during the hands-on session, but it's because Haskell's kind of mixing in some strictness that's not in what I've got on the board. Yeah, yeah. So that'll be like, let's definitely talk about that, but let's save it for a bit. Yeah. Okay, good? Yeah. Uh-huh.
What does it actually mean for the product type to be defined?
Oh, so I mean, this is the bottom, sorry. Right, remember bottom is just notation for fix x colon tau 1 cross tau 2 is x. Right, so that's an element of every type. That's not a type. Yeah. Good? Okay, so what we've seen is that a call by name lazy language naturally has products. Now the question we want to do now is flip it around and say, does a call by name lazy language naturally have sums, right? Coproducts. And so the important point there is that in a call by name language, you have to think of these variables as ranging over computations of tau 1, right? Because in the fixed point construct, we say fix x is e steps to e with fix x is e plugged in for x. Or in the beta reduction rule, we say lambda x dot e applied to e prime steps to e with e prime plugged in for x. Okay? So what we plug in for a variable is an expression. What is an expression? It's a computation that may diverge that's trying to produce a value. Okay? And that's the key to understanding what's going to happen with sums. So for example, suppose you have the function, which one did I want to do? Lambda underscore dot true versus lambda x, if x then true, else true, that we talked about before. Well, if we consider those as open terms, what we're asking is, if I have a variable x of type 1 plus 1, is x the same as if x, is true the same as if x then true, else true? Right? And the intuition we had at the beginning was, well, when x is true, they're both true. When x is false, they're both true. Therefore, they should be the same. Yeah. So if x diverges, this program of type bool terminates, and this program of type bool diverges, and those are different, right? So if we adapt our notion of contextual equivalence to this kind of setting, at bool, we will say that two programs at bool are equal if they both terminate to the same value or they both diverge. Okay? So these two things, which are supposed to be equal for this to be a coproduct, are not equal. And you can see similar kinds of problems for any kind of coproduct or natural numbers or lists and things like that. That is, your data doesn't have the universal property that you would expect. And the reason is exactly this. You don't really have an assumption of bool here when you said you had an assumption of bool. What you have is an assumption of a computation of a bool. And that's not the same as a bool. Okay? So there's this nice duality where you have products here, but don't have sums. And then we can flip things around and look at the quickly look at the call by value eager version of PCF and see that we'll have sums and not products. So the way that that works is that, so now this was the call by name lazy version of everything. So now suppose we want to tell the whole story in a call by value eager setting instead. So the first issue is that remember, we had this kind of setup to begin with. And we said that fix x is e steps to e with fix x is e plugged in for x. Okay? So if we're in a call by value setting, the key thing we want to say is that in this kind of setting, variables stand for values. Right? That's the whole point. Call by value means variables stand for values. Well, this is not a value. So it doesn't make sense to plug in fix for x if the demand is variables stand for values and fix is not a value. Okay? So there's different ways of resolving this, but one is to say we're going to restrict fix to, let's say, function, and we could also have product if we want, types. So if you do that, if you say, instead of having a recursive definition of a value at every type, we only have recursive definitions of values at function type, then what you get is kind of a combination of fix with lambda, which we can write as fun f of x is e, which has type tau1 arrow tau2, if, assuming that f has type tau1 arrow tau2 and x has tau1, then e has tau2. Okay? So what is this? If you combine, if you restrict fix to be only taus that are of the form arrow, and then build in a lambda x here to get that going, what you get is a construct that's very naturally a recursive function. Okay? So the way that you can understand recursive functions as coming up is you take the general fix, and then you say, I'm in a call by value setting, so I want to restrict it to only substituting values, which means I'll restrict it to a function type. You can do the same thing for record types to get mutually recursive functions, and the method thing that we were talking about before, the recursive object thing that we were talking about before, and then you get this. And so how does this step? Well, fun f of x is e, when applied to a value, will step to the body of the function with fun f of x is e plugged in for f, and with v plugged in for x, and fun f of x is e will itself be a value. Okay? So because we've restricted ourselves to fixed points, where the fixed points of values that will create values, we'll only be plugging in values variables. Okay? That makes sense? If I only plug in values for variables here, then I maintain the idea that variables stand for values. And then if I come back to this issue, then if this is standing for values, well, on true it works and on false it works. And true and false are the only values of type bool. Okay? So in this kind of setting, our sums will actually be sums. Our coproducts will actually be coproducts, because the kind of map we're considering when we have a term with a free variable is ranging over values, not over computations. But dually will have broken products. Okay? Our products will not have the eta rule that we said before, because, well, for dual reasons, when you think about running an eager product, then what we said before won't hold. Okay? So there's a nice theory of duality of computation that a lot of people have worked out, where I think I had it on the board here. Well, it's gone now. But the Levy work and the Zeilberger work and stuff like that, where to sort this all out properly, what you really want to do is distinguish between different kinds of types, which people call value types and computation types, or positive types and negative types. It has a connection to do with something called focusing in logic. And if you sort all of this out using these different kinds of types, then you can talk about both of these kinds of things in the same setting. So you'll have a notion of map from computations to computations, and that notion of map will have good products. And you can talk about a notion of map from values to computations, and that notion of map will have good coproducts. And so you can get the two to play nicely together, but you have to be careful about what the evaluation order is and distinguish between different notions of map so that you're talking about things having universal properties relative to the right notion of thing so that the things actually hold. Okay, so you can view it as a trade-off, or you can read up on this work on sort of making the two fit together in a nice way. But the important point is that when we're in a setting where we have general recursion, evaluation order matters, right? Whether or not a program terminates will depend on, is it call by value or call by name? Is it lazy or eager? And this has consequences for the equational theory of your programs, and that has consequences for which universal properties you actually have for your types or not. Okay, so the teaser for next time is that what we did today was to introduce fix as kind of a weird construct by itself, right? And then we kind of ad hocly integrated it with functions to get call by value going. For every type that we've seen so far, like arrow and cross and 0 and 1 and nat, we could divide up the world into introduction rules and elimination rules. We had lambda and application, or pairing and projection, or for plus, we had injections and case analysis. Or for nat, we had 0 and successor and case analysis or recursion. So fix kind of sticks out a little because it's neither an intro nor an elim, right? It doesn't make a value of a type. It doesn't consume it. What's going on? Okay, so the teaser for tomorrow is we're going to look at another kind of type that will let us express fix as an intro elim decomposition and sort that out. So it's not, doesn't have to be kind of its own axiomatic thing. We can make it fit the pattern, but it'll take a little bit more work. Okay, thanks.